Whew. All right. Mic test. Right. Okay, so let's put on this boring music. All right. And class, we've got class isn't here, I guess. Okay, so I'll just talk to the void for a moment. So we're in the middle of very important definition, which is that of a group action. So if you want to know what to expect in the next quiz, lots of questions, basic questions about group actions. Test your understanding of that concept. So, and I'll assign the homework later today, as long as I remember to do that. So yeah, this is a absolutely important concept, and so if you get off the boat here, it's gonna suck. Okay, class is here. Count as inaccurate as usual. Okay, good. Okay, so thank you. All right, so what we have to do is define two absolutely critical notions, two vocabulary words for today: orbit of a point and the stabilizer of a point or an element. Okay, so here's the setting. Let's go. The setting is the following. Setting. G acts on a set X. Yeah, that's the setting. We have an action of a group on a set. And the shorthand way to write this action is if G is an element in G and X is an element in X, we have G dot X is possibly another element in X in the set, and this dot operation obeys some axioms like this, like product G of GH dot X is the same element as this, and identity dot anything okay, identity doesn't push any of the points around. G acting on a set means the group G pushes the set X around. It jumbles the set X according to individual elements in the group G. That's what an action is. And then you have other things like if G dot X is a point Y, then G inverse dot Y equals the point X. All right, and it's the if and only if type thing. So the group G systematically shuffles the set X around. That's what a group action is, and we're just going to denote the action by a little dot. It's very important that you realize that this dot is not group multiplication. This dot is group action dot, because you're taking an element of a group and then an element of this other set X. You're combining them to create a new element of the set X. Okay, so when you have this situation, in this situation, you get the following definitions. 1. Pick any element X. Okay? Notice how you have to start. Given a single element in the set, now you get these two notions. Definition. The orbit of the element X denoted in various ways. Some people will write the whole group dot X, or simply orbit of X, or O of X. Many different ways that people will denote the concept of the orbit of a point is the subset of the set that's getting acted on is a subset of X defined as follows. G dot X is the set of all elements that are obtained from little x by hitting little x by all elements of the group. So the way you read this is hit x with all elements of the group. And see see what subset you get. Notice that the orbit is a subset of X. It's very confusing because I'm not seeing. Okay, yeah. The orbit is a subset of the set X. Okay, I'll explain why it's called an orbit. I'll try to give my explanation for why it's called an orbit. The fundamental reason is just that old people made up these definitions. So that's the basic fact of life. That's the concept of an orbit of a point. Okay, definition 2. The stabilizer of a point in the set X on which the group is acting is denoted. Okay, so denoted. Usually it's denoted stab X. Alright, stabilizer of X. But this is confusing, but it can also be denoted also sometimes G sub X is the subset of G of the group, defined as stabilizer of this element is the set of G's such that G does not move X. The group elements that don't push X to other points in the set X. The elements that stabilize the point X. The elements that don't act, that act trivially on the point X. All right, so this is a subset of the group G. All right. So the very first simple observation, easy observation. The stabilizer of an element is a subgroup. Not just an arbitrary subset. And the verification is very simple. Using the axioms of the action, the concept of action. Okay? Using this, you can see that if two elements stabilize X, G and H, then their product will also stabilize X. Just chase these axioms, and the stabilizer forms a subgroup. So every time you pick an element in the set X on which a group is acting, two things are immediately born. A subgroup called the stabilizer of that point, and a subset of X called the orbit of that point. So now I'm going to give you some funny example. Let's do a funny example that this is the example that justifies the terminology, at least of orbit. Okay, so here's the best one I could come up with. All right, so let's do this example. G is the circle group, or also known as the group of all rotations around the origin. Not just 2 pi over n or whatever, just all continuous, all thetas, all rotations around origin. All right, that's the group G. Okay, and what's the set that G is acting on? X is R2. And what's the action? The action is g dot an element of x equals rotate x according to rotation g. Just the obvious action. Rotate the plane by a specified rotation in the group. Rotation group acts on R2. All right, so let's draw R2. Let's draw our picture of R2. Please draw a straight line. Thank you. Awesome. Okay, here's R2. And I'm gonna pick my favorite point X. You know, so that you don't think all elements are called X. Here, I'll choose a different name. I'll choose Z. Here's a point Z. This is a point in my set X. All right, and now what I'm gonna draw for you is the orbit of the point Z. All right, here's the orbit of the point Z under the group, the whole circle group. The blue set is the orbit of Z. Okay, so that's exactly all the other points in the set which are obtained by hitting Z with an element of the group G. In other words, rotating Z around. All possible ways. You'll trace out exactly this subset. All right? And the second thing is that the stabilizer of Z is simply the trivial subgroup. Equals just like identity. Trivial subgroup. That's because you can't rotate by any amount between 0 and 2 pi. That's what I mean by the rotation group, by the way. Just rotating by 4 pi is the same effect as rotating by 2, whatever. I'm thinking of angles only between 0 and 2 pi. So, yeah, you can't rotate Z you can't rotate Z by anything other than 0 angle to keep Z itself. Okay? So, the stabilizer of this is trivial. But there's some other points. What if you looked at this point? Let's call this point W, the origin. So now, let's draw the orbit of W. Okay, I'm gonna draw it. I drew it. Orbit of W is just W itself, singleton set. W doesn't move anywhere else under any rotation of in the circle group. Okay? So orbit is W, but the stabilizer now the whole group. The stabilizer is the whole group. Every rotation fixes W as a point. Right? Oh wow, I don't know what happened. That was scary. Okay. It was Melko. Definitely was Melko. Right when Melko shows up, a bunch of bots just ruin our stream. Okay. So now you see why, this is what I'm going to say. You're wondering, students, why was the word orbit used? It was because of this example. Like, look at this. Look at this. Look at the orbit of this point. Um, oh no. You get the idea. This is orbit of y. Literally by the definition. Okay, and you get these little circles as orbits. Okay. So that's the example I'll show to justify the notation. Okay. All right. So now what I'm going to show you is the fundamental theorem about the relationship between orbits of the orbit of a point and the stabilizer of a point. Okay. So there is a fundamental relationship between the concepts of orbit of a point and the stabilizer of a point. Now notice that these are subsets of different places. One is a subset of X, the other is a subset of G, subgroup of G. Okay. So I'm going to state the fundamental correspondence. So the name of this fundamental relationship is called the orbit stabilizer theorem. It states the following, okay? It states that there is a natural bijection between left cosets of stabilizer of a point. Subgroups have left cosets. That didn't change over the week. There's a natural bijection between left cosets of the stabilizer subgroup and points in the orbit of X. There's a natural bijection between these two sets. They are, and in particular, if both sets are finite, these two sets, left-hand side and right-hand side, have the same number of elements in that finite case. So in particular, just a little, if you believe that there is a natural bijection between these two sets, then in particular, if both sides are finite, then the size, the number of left cosets of the stabilizer subgroup is equal to the size of the orbit. All right, how big the orbit is the same as how big the number of how many left cosets does the stabilizer have. All right. Your crush bijected you last month. Oh, I'm sorry to hear that. That is sad. Everyone goes through that. It's a it's an opportunity to grow and move on. Okay? Yeah. Okay. All right. Yes. Wait. Where? I don't know what wig you're talking about. Actually, my bad. Okay. So let me show you this bijection. Let's witness that there is such a bijection between the orbit, the set called the orbit of the point X, and the collection of left cosets of the stabilizer subgroup. All right. So how to get to that? How to witness this bijection? All right. So first, let's construct the map we'll construct a map from the group G to the orbit of X. Step 1. Consider the following function. It's just a function. It doesn't even make sense to call this a homomorphism because look at the objects involved. Just an ordinary function, f, from the group G to specifically the orbit of the given point X, which we were sort of paying attention to throughout the whole discussion. Okay? I'm going to construct this function. Now, you can't just write an arrow and put an f next to it. You have to tell the person what the function is. The function's rule is this. F of an element G is simply G times this fixed point X that we have like circled as the point we're studying. Okay? So it's, in other words, the function is given an element in the group G, hit X with G. Move X according to G, and that output point is the output of the element G. All right, so f of G is simply G times X. You can call this the action map, if you'd like. The action function. The activity function. All right, good. So there's this function, and observe. By definition of orbit, the function f is surjective. It's surjective onto the orbit of X. That's by everything in the orbit is G times X for some G. So that's just silly. It's a silly observation. Okay, number 2. No, let's now look at different points in the orbit of X. Okay, and we'll ask, what are the preimages of points in the orbit of X? So you ask. Step 2 is you ask the question. For each element in the orbit, what is the set of preimages, the set of elements that map to it under F? This is the set of G's such that f of G equals Y. But let me unravel that for you, such that G dot X equals Y. It's the set of G's, set of group elements, that when you hit X by that group element, you end up at this Y. So what is the preimage of a particular point in the orbit? It's this set. Right here. My pen went flying. So in particular, for example, the preimage of the point X itself is simply the stabilizer. Because after all, it's the set of G such that G times X is X. All right? So we know one fiber. We know one preimage of this function G. All right? So I'm going to draw a picture now. I'm going to draw a picture real fast. G, F, and then sort of orbit. And in this orbit, there's this our element X, but there's all kinds of other elements too. And for each element in the orbit, what I'm interested in is the preimage. All of this stuff It's the stuff that under the mapping went to y. And in here, the stabilizer of x is exactly the stuff that went to where the function outputted the point x. And what I want to think about is how the group G is partitioned into individual pre-image subsets. So that's the idea. Think about what are the pre-images of different points in the orbit. So that's the second thing you do. You ask, what's a pre-image? One particular pre-image is the stabilizer subgroup itself. But can we describe the other pre-images? Let's try to do that. 3. What is the pre-image of y more specifically? Well, here's what we know. Since y is in the orbit of x, we know there exists some element which I'll call A, just to use this different symbol. There's some element in the group such that A dotted with x is y. We know that we can get from x to y by a group element. That's what it means to be in the orbit. And now what I'm going to observe is the following. Observe that the entire left coset it's a left coset. The whole left coset is contained in the pre-image over y. The whole left coset is contained in this pre-image. Let's verify that. Indeed. If A times H, if H is an element in the stabilizer, then check this out. AH, which is exactly the types of elements in the left coset corresponding to A. AH times the letter X times the element X is, by axiom of group action, but H is in the stabilizer, so H dot X is X itself. So AH dot X is A dot X, which is Y by hypothesis. And so A times AH is in this pre-image over the point Y. All right? So the whole left coset of this one element A is contained inside this fiber. All right? So and now what I'll do is I'll prove the opposite inclusion. Suppose now that some element B was in the pre-image of Y under the action map. Let me write that out for you. In other words, B times X equals Y. In other words, suppose B is some element that when you push x by it, you get to y. Okay? We will show that B is in this same left coset that we invoked earlier. Okay? So, then B dot x is A dot x. Because A was also some element that we chose earlier in this paragraph. A was just some element that pushed x to y. But let's say B is some other element, okay? Or just let's say B is some element. It could be equal, could be different. All right, so we would know this equality. But then, okay, now I got to think about this. Which way do I want to put the inverse? But then B inverse A times x is x. Because act by B inverse on both sides. So act by B inverse on both sides. Oh no, did I do this the wrong way? I did it the wrong way. Let's act by A inverse. You're always gonna get one or the other. Start over. Act by A inverse. Okay, then purple, new stuff. A inverse times B times x is x itself. So now act by A inverse on both sides. You have to forgive me, this happens all the time. Okay, A inverse. All right. So now, oh, but look at this. Look at this. In other words, A inverse times B is in the stabilizer. Subgroup. Or to put it another way, B is in A times. All right? So look, I mean, this should be clear by now, but like, look, A inverse B equals H for some H in the stabilizer. So then B equals A times H, which is exactly what it means to be in this left coset. This parallel shift of the subgroup. This particular left translation of the subgroup. That's what it means. Okay? And so, indeed, all right, so let me put it all together. So in conclusion, the preimages of the action map are precisely the left cosets of the stabilizer subgroup. All right? That's exactly what the preimages of different points of points in the orbit are. So in particular, so therefore, the function which takes a point in the orbit and outputs this function which takes a point in the orbit and sends it to its pre-image under the action map, that is a bijection. This is a bijection. Is the desired bijection. Okay, so the concept of left coset of the stabilizer is in some sense exactly the same notion as translates of the point X under the group action. The different locations that X will visit under the group, those locations are encoding perfectly the different left cosets of the stabilizer subgroup in the group G. Those two notions are in perfect alignment. All right, so let me write a conclusion. So this is the proof. This is the proof of this orbit stabilizer theorem. So there's a conclusion, another conclusion. If G is a finite group, then the order of G is equal to the size of the stabilizer subgroup times the number of elements in an orbit, in the corresponding orbit. So you'll see this as sometimes if they only talk about finite groups, you'll see this conclusion from the more general fact that the left cosets of the stabilizer group are in natural bijection with the points in the orbit of X. This is a much more general fact from which, in the case where G is a finite group, you get this kind of number theoretic conclusion. So why is this? Because the number of left cosets is simply the ratio, also known as the index of the subgroup. And so, so the orbit stabilizer theorem said orbit stabilizer says that these two sets have the same number of elements. So that translates into this quotient equaling that number. All right? This kind of if in the presence of a finite finite group, the set X doesn't have to be finite, but the group G has to be finite. Notice if the group G is finite, then of course the orbit of a point will also be a finite set. You can only visit at most finitely many other points. Okay, so this is all very abstract, but what I want to show you is that, so what you should know, students, is that the notions of orbits, stabilizers, and their fundamental relationship with each other, which we just went over in a 45-minute class, then that language and that relationship are just ubiquitous in mathematics. You can't become a mathematician without knowing these terms. Like, you won't be able to read a single paper, especially any paper that's in 75% of mathematics. So it's just like, that's one reason for the math majors and especially the grad students to just pay attention to these constructions. But I want to actually go the other way. I want to take you back to 8th grade. I just want to take you back to 8th grade, just for fun. Let's go back to 8th grade. And the way I'm going to do that is I'm going to pose an 8th grade math problem. All right? Look at this. It says, in how many different ways can you arrange 3 star magnets, 4 square magnets, 1 circle magnet, and 5 triangle magnets in a row on your refrigerator, like this. Like, for example, this is one way. How many different ways are there? All right, yeah, it was traumatic, but what I'm gonna do, Tropical Geek, is either I'm gonna make 8th grade even more traumatic, or I'm gonna show you that there is a one grand principle called the orbit stabilizer theorem, which underlies so many diverse settings, including these permutation combination type problems that you might have had a hard time with. There's actually one very basic grand conspiracy in which these separate little topics become unified. That's actually the goal of a mathematician, to see that actually there's fewer ideas that are manifesting in many different ways than just a whole bunch of encyclopedic different memorized facts. That's the reason why there's an abstract algebra course. It's the fundamental reason. Okay, so here's the problem, and many of you might just know, like, okay, what you're supposed to do, you might just know. You know, you get that note card from 8th grade, your 8th grade math note card, and you just probably know, oh, what you do is you do, it's this. This is the total number. All right? Yeah, so Ryan probably just did this and just wrote this down, and yes, that's correct. But what I'm gonna show you, what I want you to realize is that, okay, yeah, he did it wrong too, and then he fixed himself. Typical Ryan. Okay, so what I want you to do is, what I want to do here is realize that this is an instance of orbit stabilizer. The orbit stabilizer theorem. Here we go. Here's what we do. Look at the group G, which is S13. The scrambling of 13 things. But what are the things? The things are going to be the location. First, second, third, fourth, fifth, sixth, 7, 8, 9, 10, 11, 12, 13. The little locations, 1 through 13. The group is S13. The set X is the collection of all these strings. All possible strings. Okay, we're going to call this strings. A string of 3 stars, 4 squares, 1 circle in there, and 5 triangles. All conceivable possible strings. That's a set. And now the point is, first observation, the group G acts on the set X. Via permute the string. Oh, you gave me a permutation? And a string, little x? Here's how you combine them. Do this permutation to this string. You get a new string. That's typical group action situation. All right? And now let's observe something about this group action. Observe. X consists of a single orbit. Namely, meaning any one string can be hit with a permutation to produce any other string. That's by definition, right? Any one string, there's some permutation of it to create any other string. That means that by permuting any one string, you will visit all other strings. In other words, there's one orbit that just sweeps out this whole set. There's a word for this phenomenon. Okay, there's a word for this. In other words, G acts transitively. On the set X. There is only, every point is equivalent under the G action, or every point is obtainable under the G action from any other point. One grand orbit. All right. So number two. Number two. Pick your favorite string. For example, this one. How many squares were there? Just put them all next to each other. Okay, this one. The stupid string. The one that's cleanest. Okay, pick your favorite string and ask, what is the stabilizer? Which permutations maintain this string? Which permutations maintain this string? Answer. Answer is, the stabilizer is, yes, identity of course, but there's tons more. There is S3 cross S4 cross S1, which is just singleton, cross S5. Okay, what do I mean by this? I mean, to write it very, very concretely, it's the set of permutations of the following form. 3 cycle? No, not 3 cycle. Only involves 1, 2, and 3. Only permutations involving 1, 2, and 3. That's like S3 sitting in there. Okay? Times only permutations involving 4, 5, 6, 7. Etc. You have to have a singleton here. And 8 has to go to 8, folks. Okay? So in cycle notation, you wouldn't even see an 8. Right. And then put next to that any permutation involving only 9, 10, 11, 12, 13. And if you ask how many such permutations are there total, it's S3 times choose an S4 times choose an S1 permutation and choose an S5 permutation. All right? So the stabilizer is a copy of the group S3 cross S4 cross S1 cross S5 embedded, there's a homomorphism embedded inside of S13. It's that subgroup. Okay, but now what's the size? Well, that's 3 factorial times 4 factorial times 1 factorial times 5 factorial. And the orbit stabilizer theorem says the size of S13 divided by the size of the stabilizer is the number of elements in the orbit. In the orbit. But the orbit is the whole set. Thanks to the transitivity of this group action. Done. We were trying to count this number. And so, what you see is that the whole business of permutations and combinations is just one incarnation of a much general and simpler. Like, the more general a thing is, the less content it has. Think about that carefully. The more general a fact is, the less content it has. The more specific a fact is, you gotta have that encyclopedic mind to keep all that in your mind. But the more general you see that, oh, this is a mere manifestation of orbit and stabilizer, mathematics starts like shrinking in a sense, starts getting unified. All right, so 8th grade was orbit stabilizer. That's the lesson you want to learn, but learn that it's just one instance of orbit stabilizer. Okay. Okay, so what I was gonna do next, next up, there are certain group actions. I know the time's over. Just watch the video afterwards. Next up, and this is what I'll do next class. There are certain group actions which are more important than others. All right, so the type of actions I will introduce next class, they will be the ones that are used in group theoretic arguments a lot. Okay, so these actions are of the following general shape. A group G acts on, and then the thing that it acts on is something kind of related to the group itself. It's going to be a tongue twister type situation. It's going to be like like the Cayley theorem. It's going to be an action of a group on something involving itself. Okay? It acts on, e.g., itself via left translation. I think I got this right. There's another one that's commonly occurring. Itself via something called conjugation. And this is one very important action of a group on itself that I will have to explain next class. But there's a lot more than this. Like, for example, a group G acts on the set of all subgroups. Via the same conjugation action. All right? And the list grows, and which action will be useful for you to analyze when trying to prove which theorem, general theorem in group theory, depends on the context. But one basic tool that will always be used is the orbit stabilizer theorem, no matter what the action is that you're considering. Okay? So that's the game plan for the next lecture. Certain very important kind of intrinsic or self actions of the group on its own self, or on objects constructed within itself. That kind of inner reflection, inner action is those are the basic building blocks and tools that many group theory theorems rely on. So that's the kind of thing, those actions are the ones we'll have to discuss next time. Okay, so let me look at the chat for quick questions and see if there's anything that jumps out at me as important. Okay, does not understand. Oh, you don't? Okay, so that's good to know. Oh, thank you all for following. Sorry, Meme Lord, Eva, Asian, okay. Meat. Shungite was redeemed a long time ago, so they're probably gone. But Meridian, here's your Shungite dose for the day. Let the 5G not disturb you today. Tropical has their... Okay, Tropical, this is yours. I might have gone counterclockwise. This might actually cause extra 5G to interfere with you today. I'm very sorry about that. I don't know which way you're seeing the rotation, so that's unfortunate. Okay, Professor Melko was here. Good. I hope he's not here anymore. What else? Holy cow, what is happening? Okay. Lots of bots tried to ruin our stream. Hilarious. I hope the bots didn't like show up on... Did they actually show up in the chat? I hope they get banned like automatically somehow. Maybe that's just too much to ask for. That sucks. What a ripoff. Oh yeah. Yeah, okay. Yeah. Yeah. You get extra 5G radiation. Okay, good. So can I wrap the next lecture? Yeah, I know. Sometimes my words are in alignment with the music. That's hilarious. So no, I can't wrap the next lecture because it's not something I do consciously. I just naturally rap when the beat is at 60 beats per minute, I guess. Okay. All right. Awesome. Okay, so folks, go take your favorite finite group for fun. Act on come up with an action of a finite group on some nice geometric thing, if you like geometry, and go and investigate different orbits of different elements. Notice the relationship between the size of the orbit and the size of the stabilizer. They will be in some kind of inverse relationship. They're related by the orbit stabilizer theorem. But you should witness it for yourself in examples. I'll try to do more examples on Friday, but I am racing against the clock. We'll definitely do way more examples in Friday's office hours. As many as students want to see. I can just play around trying to come up with actions of groups on various sets and just take you through a tour of how many there are. Kind of ubiquitous situation. All right. Finite simple group of order 2. Well, I don't know. So I don't know if I can learn that on the recorder. I know what you're talking about. I wonder if that band is still playing. I think the band is no longer together. So I forgot what the name of the band also had a funny name. Maybe it was called the Finite Simple Group of Order 2, and then they had various songs that were named other things. I forget, but yeah, it's a very long time ago. That definitely dates us. For the... Yeah, definitely. That was a long time ago. That was before the era of Chegg and Math Overflow, when we had to do our own homework. It was a different time. It was a different world. Right. There were only like 3 YouTube videos, and one of them was this one. Yeah, I remember that time. I remember. Okay, time to go. I have to learn some calculus real fast, folks, and eat. So I gotta do that. And thanks for showing up to class, students. And I will see you guys Friday. And students, probably show up on Friday's office hours to see more examples, because where am I can't take up this time for examples, because then we will never get to the theory. And the theory is in some sense harder than the examples, so I have to put that somewhere. And so class time is devoted to that. Okay. You guys you should also discuss explicit examples on Discord. Just so you understand, Sloth does a lot of this. But just to understand, see if you're understanding the basic concepts through examples. And you know that my true and false questions, they're heavily example oriented. So the more you can play around with, the better. Okay, so let's send all of you to New York City. All right, go check out New York City from a bicyclist's point of view, a delivery person point of view. All right, we're gonna go over and check out New York City. All right, let's go do that. Let's see what's happening in New York City, folks. Tell New York City, spread the word that there is a simple, basic relationship between a stabilizer of a point and the orbit of a point. It's captured by the orbit stabilizer theorem. Go share that with New York City. All right? Here we go. Get ready to raid. Get ready to spread that knowledge. New York City definitely does not have anybody in it that knows. Hey, Tom Thinks. Thanks for following. If you're the same Tom Thinks, it's amazing that you followed. I love I think if you're the same Tom Thinks, I love your channel. It's hilarious. Everybody go check out Tom Thinks. Check out Raid. Yeah. Everyone check out Tom Thinks. Wait. Okay, Tom Thinks is probably not online right now, but Tom Thinks is best, like most unique Twitch stream. And I'm a close second. And then at number 5,000, I think, is Professor Melko. Just to give you a sense of the landscape. But Tom Thinks, dude, I love what you're doing out there. That's, oh my god, just so awesome. Yeah. Okay, Melko, yeah. Hi, I didn't know you were still here. Okay, let's go show New York City that 8th grade was simply one manifestation of the orbit stabilizer theorem. All right, let's get out of here. Did it raid? Did it finish? Is it over? I think it's raided. Oh my god, I am so bad at raiding.